Okay. Hello everyone, my name is Kelton Kearsley, and today we're going to be talking about electric field lines and equipotential lines. Now to start off, I want to give a brief introduction / demo because those are cool, right? So what I got is I got two different pieces of tape. One's a positively charged piece of tape and one's a negatively charged piece of tape. Pretty easy, you can do it at home. Just put two pieces of tape on the table and pull them apart, and you got different charges of tape. But what I'm going to do is I'm going to put a negative charge on this rod, and we're going to see how this affects the two different pieces of tape. So as you can tell, our positive charge is attracted to our negatively charged rod, whereas our negatively charged piece of tape is repelled. So two opposite reactions or interactions with this rod. So the two forces that are acting on the tape that we see can be explained by drawing the field lines that represent those forces. So electric field lines represent a force experienced by a point charge at a certain distance from the source. Electric field lines also show the direction and magnitude of that force. So let's start with this first positive charge that we have here. So we're going to put a point charge out here somewhere, and we're going to draw the lines of the force that come from this source, which is a positive charge. So these forces would come pointing outwards, whereas if we were to put a point charge with a negative source, we would see these lines being pointing in towards the negative charge. So something that helps me sort of remember the direction of these is just remember that positive people, they're always outgoing and always reaching out to other people, whereas negative people, they're pretty focused on themselves and sort of self-centered. So that is one thing that helps me. Hopefully it helps you. Sort of fun to tie physics into real life, you know, it's all related. So that's sort of cool. Another thing to keep in mind is the magnitude of the force can be represented by the number of lines that are drawn. So let's say this source, this positive charge down here, has a greater charge than the one above it. So we would represent that with a greater number of electric field lines. So because it has a greater charge, it will produce a greater force. So the next thing that we'll go over is what happens when we have multiple charges. So in the first case, we have two of the same charges, and what we saw in our demonstration was when we put the negatively charged rod close to the negatively charged piece of tape, we saw that they repelled each other. So how would we draw that? First we're going to draw like this imaginary line in between them. And since they are the same charge, these electric field lines will want nothing to do with each other. So that's why we get this repulsion state. And remember, they're negatively charged, so they're pointing in. And that's where we get this repulsion. The next thing is with opposite charges. Like we saw in the demonstration, the positively charged piece of tape and the negatively charged rod came together and they were attracted. So, like the saying goes, opposite charges attract. We see that these field lines start at the positive charge and end on the negative charge. So an application to this, if we wanted to see what the electric field would be at a certain distance from our source, we could use this equation right here, E equals K times Q over R squared. So E is equal to our electric field, K is a constant, it's always going to be 8.99 times 10 to the 9th. Q is our point charge of our source, and R is the distance from that charge. So I have this practice problem here, and it asks what magnitude point charge creates a 10,000 newtons per coulomb electric field at a distance of 0.213 meters. So I have my electric field that's given to me as 10,000 newtons per coulomb. We're also given our distance, our R, which is 0.213 meters. And then we also know our K, because that's our constant. So we're trying to find what the point charge is. So I write down our equation here. E equals K, absolute value of Q over R squared. Now I'm going to do a little bit of algebra in order to solve for Q, and then we'll plug in all of our numbers that we have. So first I'm going to multiply both sides by R squared, and that's written E R squared equals K Q. And I'm going to divide by both sides by K to get our Q by itself. And that's rewritten ER squared over K is equal to Q. So if we take in all the information that we already have and plug that in, we will have 10,000 newtons per coulomb multiplied by our distance, 0.213 meters, and that's squared, over our constant, 0.99 times 10 to the 9th newtons times meters squared over coulomb squared. And when we plug that in, we get 5.05 times 10 to the negative 8 coulombs. And that's equal to Q. So from the question on the previous slide, we found the point charge of the source. And we found that it was 5.05 times 10 to the negative 8 coulombs. We also know that at the given distance, which was 0.213 meters, we know that the electric field equals 10,000 newtons per coulomb. And that's as long as we have that distance anywhere around that point charge. So we can draw that by a circle right here. And this circle is what we call an equipotential line. And equipotential lines represent where the electric potential or voltages are the same. And because the electric potentials are the same, we know that it requires no work to move a charge along that equipotential line. So I can explain that by using these equations that we have here. So this is our electric field equation here, and very closely related is our voltage equation here. So V stands for voltage, and we know that our K is our constant, Q is the point charge, and R is the distance from the source. We also know that work is equal to the negative change in potential energy, but is also equal to the negative charge times the change in voltage. So if we were to plug in what we just solved for Q, our 5.05 times 10 to the negative 8 coulombs here for our Q, we'd plug that in and multiply that by our delta V. But if we can see here, this is the same Q. If our distance didn't change at all, then our voltage wouldn't change. So our change in voltage in this case would equal 0, which would then, when we multiply those two together, we'd also get 0, meaning that it would require no work to move that charge along that equipotential line. So when we draw equipotential lines, it's pretty simple. One of the main rules is that equipotential lines are always perpendicular to the field lines. So when we draw equipotential lines, that's why we get this circle pattern. It's because the equipotential line is going through all these field lines perpendicularly. Another thing to note is that the further away we get from this point charge, the smaller the voltage will be. So if we look at our equation here, V equals KQ over R, if we increase our distance or increase our R value, then our V value will decrease. Our electric potential or voltage will decrease. So if we draw a equipotential line that's closer to our source, this equipotential line will have a greater electric potential than this equipotential line. Another thing to know is that the closer the equipotential lines are, the greater the rate of change will be. And I'll talk about that later in the other slides. So if we have multiple charges, that will sort of change our equipotential lines from looking just like our plane circle to looking a little bit more different to something like that, like a little Ninja Turtle with a mask. So just remember that with the equipotential lines, they represent a place where the electric potential or the voltage is the same. So that's all that this is happening here, even with this crazy shape. But if we have two of the same charges, like what we have here, two negative charges, we'll get this looking shape, and it'll be the same for if we have two positive charges. But if we have two opposite charges, that sort of changes here to where we have these more oval looking equipotential lines. Notice how there's sort of like this barrier here. That's because we're going from a positive electric potential to a negative electric potential on this side because of the two different charges. And if we look closely, we can see that there's like this smaller difference, or the lines are closer together on this side in comparison to this side over here. And that's because where the lines are closer together, like I said earlier, that's where the rate of change is greatest per distance. So something that helps me to understand this or visualize this is a topographic map. If you guys have ever had to look at one of those before, it has like all these crazy lines here. So the closer the lines are, that represents a greater change in elevation. So if we have like really close lines, like in this area, we know that the terrain is pretty steep. So here I have a picture of my beautiful mountains, the Grand Tetons, and you can see here that right here is extremely steep, and if you've hiked that, you'd definitely be able to attest to that. But that would be represented by these super close lines here, showing a great change in elevation. Whereas this place down here, where it's a little bit of an incline but not so steep, would be represented by these more spread out lines. So to summarize what we talked about in this video, the electric field lines represent the direction and magnitude of forces experienced by a point charge at a certain distance from the source. We are able to use the equation E equals K times Q over R squared to solve for the electric field, the point charge, or distance. Also know that with equipotential lines, they represent where the electric potential and voltage are the same. And also with equipotential lines, the closer the lines are, the greater the change is over a shorter distance. Just like how we saw in the topographic maps, the closer the lines were represented a greater change in elevation. So hopefully that helps you guys. If you have questions, please leave them in the comments below. Thanks for watching.